recording. Okay. So what we're looking at for these first 5 is I've given you a chart and we're going to figure out what the equation is from this chart, okay? We'll get into calculator stuff tomorrow, but I just kind of want to do this manually by hand, see what we know, see what we remember. Okay, if I look at the first one, there's a couple different ways that you can look at this. I'm going to start by seeing how do I change from each point? So what did I do to go from 3 to 5? Add 2, good. From 5 to 7? 2. Okay, cool. What about on my denominator on the bottom? What about my y's? How do I go from 6 to 10? Good. And from 10 to 14? 4. Good. Look at that. It's consistent. So these two are both add 2 on top. The bottom are both add 4 on top. That is a consistent change, a consistent rate of change. When it's constant like that, then I know that it's going to be a linear graph. I can think of it as y equals mx plus b. So it's going to be linear because it's the same rate of change. Okay. Let's think about it. Again, you can kind of do your little jumps, or you can even relate the two numbers together, the x and the y. How am I moving from the x to the y? What am I doing each time?
Dividing 2.
We're going to multiply by 2. If I go from the x to the y, remember we're in y equals, so I'm thinking about what do I do to my x to get to my y? I'm multiplying by 2. So y equals 2x. And I think about it, do I have any b? Am I adding anything to it as well? Am I doing 3 times 2 and then adding something to that? Or 5 times 2 adding something to it? 9 times 2 adding something to it? No, technically my b is just 0, right? So my equation is just going to be y equals 2x. That is it. Okay. Similar but different idea for the next one. Okay. Oh, sorry, Millie.
So when it goes from the 7 to the 9, that's 2 again, and the 9
Yep.
to 12, then it's 3. Does that make any difference?
Notice that this one will be plus 3. How do I go from 18 to 24? Plus 6. So I went up 1 for my x's and I went up 2 for my y's, and that's represented right here with my slope. Very good. I like that you're like, but it's not always a plus 2 and plus 4. Good luck. However, what I do want to point out is every time you were going like changing 2 in your x, you changed the same in your y, because it's going to be different on this next one. Okay, let's look at our x's here. What am I doing each time on my x's? Adding 1. And this time it is every single time I'm adding 1. Now on my y's, what did I do to get from 2 to 3? What about from 3 to 6? And from 6 to 11? 5. Is that a constant rate of change? No, this one is not a constant rate of change. And I'll tell you right now that this one is going to be a quadratic based on its rate of change. Okay, so that means it's not just going to be y equals mx plus b, it's going to be an x squared. Okay, and this is where we're going to use a little bit of thought as we go. Okay, so we have to do some kind of x squared. So I'm going to have an x squared involved, and I'm going to think about, do I need to add or subtract anything to that square as I go? Let's look at our numbers. Okay, if I plug in 0, I get out 2. If I do 0 squared, is that going to get me to 2? No, right? What do I need to do to that? We're going to have to add 2. If I do 0 squared, that by itself is not 2. I have to add 2 to it. Okay, same idea if I do the 1. Is 1 squared plus 2 going to be 3? Yeah, 1 squared is 1, plus 2 is going to be 3. What if I make it a 2? 2 squared is 4. 4 plus 2, is that 6?
Yeah.
Okay, nice. We checked our work a couple times. My equation here is just going to be x squared plus 2. X squared plus 2. We're doing some pretty basic ones right here. If there was some x's involved, it would get a lot more complicated. But we'll just keep it basic as we go. Okay. Number 3, I want to see, is it more like the linear one or is it more like the quadratic one? Okay, I have 2 to 4 is plus 2, right? And then 4 to 6 is plus 2. What about the bottom? What am I doing each time there? Adding 6. Does it say constant? Does it say consistent? Good. What does that make it, linear or quadratic? Linear. I'll think of it even a little different than the way we thought of it before. Just like before we had the plus 2 and then we had the plus 4, and now I've got the plus 2 and the plus 6. Another way that I could have thought of that first one is I could have separated and looked at just the slope. Remember, slope is your y's on top, change in your y's over the change in x's, right? What is my change in y's in this problem? It's my 6, right? It's every time I move in my Ys, I go from 4 to 10, I go from 10 to 16. That change in my Ys is 6. What's my change in X's? 2. That makes my slope here 3. Good. Which, just looking at numbers like 2 and 4 and 4 and 10, I don't know if I want to come up with that. So that's a good way to look at my change in my slope. So it's gonna be y equals 3x. And then now I gotta think about my y-intercept. Okay, on this last one, we were like, oh, well, 2 times something isn't gonna get us down, like 2 times 3 stays at 6, so we didn't have to have any y-intercept. You could do the same thing again. I could plug in, well, 3 times 2 plus or minus something is gonna get me to 4. Like, you could practice a couple points like that, just like we did before. Or another way to think of it, because I just want to give you as many options as possible. Another way to think about it is looking back at my list of numbers. See how each time I added 2? What if I had another point before this? What if I had done something and added 2 to it to get to 2? What would have that x in front of it been? 0. Good. Okay, same idea. What if I had a number and added 6 to it to get 4? What would that y value be? -2. Why is it helpful that I led you to this point?
-2 would be the B.
-2 would be my B. Why, Macy?
Because that's just like where you would start on.
That's where I would start on the graph. I think I heard it from somebody else. Somebody said, so did I hear someone say y-intercept? Because that is correct. It is your y-intercept. So we're gonna say 3x minus 2.
Why is it not for the first one though?
If I would have kept going back, you could have, I guess we could have keep seeding it. Basically, if you look at how the x relates to the y, they will only multiply by 2. You don't need to add or subtract anything to get to that y. If I go from x to y, you just multiply by 2 each time. No matter which number set I look at, you're still just multiplying by 2. We didn't have to add anything to go from x to the y. Does that make sense? Okay. And then last but not least, I've got one more. Let's look at this one. Does it look like it's gonna be linear or quadratic? Quadratic. It's definitely not linear. So let's look at this. We're adding 1 each time on top. +1, +1, +1. On the bottom, it looks like I start by minusing 3, right? What's the next one gonna be? -5. What's that one? -7. 7. Okay. Doesn't really matter. What I want to think about here is it looks a lot like the pattern that we saw earlier with that quadratic 1, 3, 5, right? When we do quadratic graphs, there's basically that pattern when you graph it. What we could do is just like on the last one on the green, on the linear one, where I went backwards 1 point, let's go backwards 1 point to help us center this graph. Where I would have started something +1 gives me 1, I would have started at 0. You know what my y value would have been if I went backwards? 40. Why is it 40? -1. Remember I said it's just like that pattern up here, right? We had the 5, we had the 3. We haven't done the 1 yet, so we got to do that -1. That's helpful because that's where I start. That's going to be my like y-intercept. That's going to be my vertex essentially. And then we know it's a quadratic. There's no value in the front of it. So we're gonna say -x². Are you okay with my minus instead of a plus? Anyone know why I put a minus instead of a plus there? We're going down. Each time we're decreasing. Decreasing, decreasing, decreasing. -x². Tomorrow we are gonna throw this on the calculator, but I didn't want to do that today, so I just kind of wanted to walk through kind of a little bit of a mental stretch with you. This is not super important. This is not something you'll see on a quiz or a test. I just wanted us to kind of work through it, okay? So if this stresses you out, it's all right. Okay, just keep it moving. Just getting our brains warmed up, all right? All right, we got a few word problems. You guys ready to move on to some word problems? Okay. This next one, it says a bakery sells a 9 by 13 cake for the same price as an 8-inch diameter round cake. Okay, we're gonna stop and we're gonna draw a quick picture, okay? I've got a rectangle and it's 9 by 13. And I've got a round. Okay, too bad if that circle that notability won't help me. There we go. A round cake, which means my diameter is 8. What's my radius gonna be if my diameter is 8? 4, good. I'm gonna go ahead and label that just because I think that's gonna be helpful. It says if the round cake is twice the height of the rectangular cake, which option gives the most cake for the money? Okay, so I'm thinking they cost the same price. I'm having a party, I would have the most amount of cake there for my guests. I want to buy the cake that has the most area, the most volume in a sense, okay? So we gotta do a volume equation. Go ahead. 13 times 9, good. That's gonna give us our surface area, our number on top, which is really good. So Alea's like, okay, we're gonna do 9 times 13. I'm gonna argue we also need that height, okay? Essentially, we're doing the volume of the cake. We care about the whole depth of this 3D figure. It tells us not exactly how tall it is. It just says the round cake is twice the height of the rectangular cake. So what would I do to represent my height for the rectangular one? What would I use to represent the height there? We can think of it as just H. You can think of it as X if that makes you happy, but it's just one of them. What about the circular one? 2H, good. Okay, so I can think of it as 13 times 9 times H is gonna be my volume, so let's multiply those two numbers together. 13 times 9. 117H, okay. That's how much you're gonna get in the rectangular one. All right, let's do the circular one. Same idea, just like we did the area of the top and then we times by the height, the area of the top of this circle is gonna be what? What's the area of that circle gonna be? Sorry, what? How do you find area of a circle?
Pi r squared.
Pi r squared. Pi r squared. So pi, what's your r here? 4 squared. And then just like we did in the other one, we're gonna multiply by the height. What's my height for this one? 2H, good, so don't forget that 2 involved there. So I've got H and I've got 2H. All right, 4 squared is 16, and 16 times 2. I also want us to multiply that pi out. I know I don't normally ask you to do that, but I can't relate something pi times 117. So we want to multiply all of that together. And so we can even do that in the calculator. I'm going to do pi times 4 squared times 2, and I'll even pull the calculator out for this one. Pi times 4 squared times 2. That's about 100.5, okay? So the volume of this cake is gonna be 100.5 times H. Which one's bigger? The rectangular one, why? It has more volume, right? 117 is bigger than 100.5, so the rectangular one is the better deal. Rectangular is better. Feeling all right with that? All right, let's look at the next one. It's a really similar idea. It says the garden shop sells 12 by 12 square stepping stones for the same price as 13-inch round stones. Okay, again, we stop, we draw a picture. Yeah, notability. My diameter here is 13. What does that make my radius? 6.5. Very good. Okay. This one though, it says they have the same thickness. So do I need to add that height in there this time? No, we can just do the area of each one and compare them, okay? So same thing, the area of this square stone, this 12 by 12 is gonna be what? Good, 144, 12 times 12. Okay. Area of my circular one is gonna be pi 6.5 squared. And again, I am gonna throw that in my calculator because I cannot compare 144 with something with a pi in it. I want it to be an actual number. So pi, oh, that's me. Times 6.5 squared. is gonna be 132.7. Which one here is a better deal? The square one, good. One's bigger, so it's better. All right, good. We practiced a little bit of area, volume, comparing, contrasting, all that fun stuff. Now we're gonna get into some equations. We're gonna do some plugging and chugging, and it's gonna be very important whether we plug it in for the X or the Y or whichever variable we go for. Okay, anybody questions yet? Okay, let's keep it rolling. Again, I know this is boring, just stay with me, stay with me. Okay, this one says at Oshkosh, Wisconsin air show, Jake Trooper drops a smoke bomb to signal the official beginning of the show. Ignoring air resistance, an object in free fall will fall d feet in t seconds, where d and t are related in this algebraic model right here. D equals 16 times t squared. Okay. Letter A says, how long will it take the bomb to fall 180 feet? Where does that 180 feet go in my equation? D, why? It's my distance, it's in feet, we just plug that in for D. So I'm gonna do 180 equals 16 t squared. That seems simple enough, right? How do I solve? Divide by 16. So 180 divided by 16 is 11.25 equals t squared. How do I get t all by itself? Square root. And since I already have a decimal under a square root, just go ahead and plug it all into the calculator. Square root of 11.25 is about 3.35. The question was, how long will it take? It will take about 3.35 seconds. All right, feeling okay with that? All right, let's do letter B. It says if the smoke bomb is in free fall for 12.5 seconds after it is dropped, how high was the airplane when the smoke bomb was dropped? Where do I put that 12.5? In for T. In for T. Awesome. Do it. Don't necessarily need as much work as I have, but you need to be able to plug things in and go from there. Okay. All right, when you're done with that, flip your paper over. You're doing awesome. All right, we are gonna skip that first one, so we will not do number 23. We've got one more word problem and then a couple kind of algebra stuff that we should remember how to solve. That is it for today, okay? Skip 23 again, we're gonna do number 47. It says Swan Auto Rental charges $32 per day plus 18 cents per mile for an automobile rental. First one, Elaine rented a car for 1 day, she drove 83 miles, how much did she pay? I know I've got a couple pers here, I've got per day and per mile. In both of these examples though, I say that they only rented it for 1 day. So you can think of that 32 per day as just a flat rate. They have to pay that 32, okay? Let's write an equation from this. Hence 83, good. If I were to write a general equation, that 83 would just be an X, right? So Leia wrote it out for letter A. I'm just gonna keep it for my general equation. Remember that the 18 cents and X go together because they're driving a different amount of miles. When we plug in for letter A, we're plugging in 83 for X. So I'll do 32 plus 0.18 times 83. And then add 32 to that, and I get $46.94. All right, cool. Letter B says Ramon paid $69.80 to rent a car for 1 day. How far did he drive? Where does that dollar amount go? In for the Y, good. So we're gonna say 6980 equals 32 plus 0.18. And then you guys can solve that, we'll minus it from both sides. That's 32 from both sides. And then we'll divide that 0.18 from both sides. And I got 210 miles. That look good to you guys? Okay, awesome. All right, you're doing great. Most of the boring part is done. The last couple are ones that we should be good at. We should know how to solve. And I'm happy to walk through them with you, or you can kind of do them on your own. Okay? Questions before I move on to that? No? Okay. All right, these two right here, they say solve algebraically, which means I want you to solve for x. Let's get everything to one side. Let's get and then we will either factor, quadratic formula, etc. to find x. Just a reminder, I like putting all my I like my x squared to be positive, so I move things to one side or the other depending on which one will give me a positive x squared. So if I have a 2x squared on the right side, I'm gonna move everything to the right side. So then I'm gonna end up with a positive x squared value. I'm minusing x squared from both sides, adding 3x to both sides, minusing 4 from both sides. And once I do that, I get x squared minus 4x minus 12. This one, I think you can. This one factors pretty easily, right? What's that gonna be?
6 and 2.
6 and 2, positive, negatives, where both?
Negatives, positive 6 and negatives.
If you solve it all the way out, yes. If I put it in factor form, it'll be x minus 6 and x plus 2. When you actually solve it to give me what x equals, x will equal negative 2 and positive 6. I don't know why I did that. Perfect. Okay. Try the next one. I don't think it was factors as well, so you might need a quadratic formula that one. I will work it off to the side, but you try it on your own. Got my quadratic formula for the second one on the board. I didn't get it to factor to anything nice. I couldn't simplify it, so that was as good as I got. All right, questions so far? Did I mess up? Where did I mess up?
I mean, maybe I messed up.
I might mess up. What do you have?
I have -7 plus minus 5 squared root 3 1 2.
5 square root 3 over 2?
Yeah.
Okay, so if you did a factor tree out for 105, let's see, if we divide 105 by 5.
I just put it in wrong.
Oh, okay. Sometimes I put it in wrong, so don't be afraid to ask. Sometimes I mess up. Okay, but that one is good as it gets. I wish that 105 went farther. I did do the factor tree last class and I was like, oh, it just doesn't. So, okay, last two, we're gonna graph in the calculator. Remember when we solved graphically in the calculator, you put 1 for x1, or sorry, 1 for y1, 1 for y2. I believe that these should very easily be able to be seen at a standard window. So I'm gonna plug them into my two equations, and then I'll find that point of intersection. So we're gonna go to y equals, I'll clear this all out. Square root of x plus 8, or x plus 6, excuse me. And then 6 minus 2 square root 3 minus x. Is that a 5? Does that look like a 5? Okay. Thank you. Square root is actually one of our BFF graphs, so that should be something familiar to you. It kind of looks like, well, actually, it is a sideways parabola, but it's only one side of one. So it just kind of zooms up a little piece up. And that's what we're gonna see on the graph. So you'll see little square root graphs as we go. But this is one reason we learn BFFs, so that I'm not surprised by these shapes. Let's see, because it looks like square root function. It only looks like they intersect at one place, so I'm gonna go second trace intersection. And I'm gonna go, mine says left bound, right bound, yours might say first curve, second curve, doesn't matter. My first, or my x equals for letter A is just at 2.66. 2.6. You feel okay about that? Okay, try the next one. Remember, if you got multiple points of intersection, you maybe have to do intersect twice. X plus 1. X squared minus 2x minus 5.
So you want,
I haven't had a commercial in a long time. Okay, so I get negative 1.37 and
We're finding zeros.
finding intersection. And 4.37. Questions on this? Most of your homework is kind of these last two sets of problems. I will tell you that the first problem on your homework kind of looks like those first few problems that we did in class. And I actually want you to skip that one because I want to do something different tomorrow when we talk about it. So number 1 on your homework, skip for now. We'll do that one together tomorrow because I'm going to teach you a calculator trick. But the rest of it you can do. Okay. We've got about 9 more minutes. I'd love for you to start your homework. I'd also be happy to do any more BFF graphs. So if you want me to do anything on the board, I'm happy to do it. That's kind of all I got. So if you want to work on your homework, go for it. If you want me to do BFFs, I'm happy. If it's not, I will put it on mine because I know I recorded it. Okay, so
You do like the last one, cosine option,
which one?
the last one. Cosine.
What's it called? Cosine?
That's not the last one.
Oh, I can do cosine.
Actually, no, I meant, I'll just.
Oh, logistic? Okay. I'd be happy to do cosine too if you want me to.
I gotta.
Okay, you got it right.
Yeah.
Here's my logistic function. I'm gonna go erase all of this. So logistic function, you can go to your textbook page and look at it. I drew it really, really big. But notice that the y value is at, the top y value is at 1. If I kept it within the graph that we had, it would be like super small. It would be like this, which just like isn't a super helpful line to me. So I drew it a little bit bigger. But note that it only goes as high as 1. Okay. A special thing is it does go through the point 0, negative, or 0, 1/2. There's no negative y's. There's nothing bigger than 1. Okay. The equation for this one is 1/1 plus e to the negative x. Kind of funky. Okay, now that we've had the graph though, I believe we can do everything else from it. Anybody questions on graph or equation before I start getting into all the rest of the nonsense? Okay. All right, domain, what's my domain here? What x is what? All real. Negative infinity, positive infinity. What about range? 0 to 1, good. Do I include 0? Are there any points at 0? Nope, are there any points at 1? No, so we are gonna go parentheses 0, 1 for my range. What about continuity? Could you draw this without picking up your pencil? Of course you could. Okay, increasing, decreasing. Remember, that's how we go across the page from left to right. So I'm gonna start on the left and I'm gonna go to the right. What am I doing? Increasing, do I ever stop increasing? Nope, I start increasing less, but I'm still increasing the whole time. So I'm gonna say I'm increasing and I'm gonna say negative infinity to positive infinity. Okay, symmetry is kind of a weird one. There is no symmetry on this graph because it doesn't go into the third quadrant. If this like was centered around the origin, it would be symmetrical, but it's not because it doesn't go into the third quadrant. So that one is no symmetry. What about boundedness? Is there a floor that I can never go below? Is there a ceiling that can never go above? We call that boundedness is both. Both above and below. Local extrema. You guys remember what the word extrema means? Like max, min, a high point, a low point. Do you have any high or low points at all here? We have some low points, but I'd argue every low point has like a point next to it that's lower. So I would say there's no any point that's higher or lower than anything around it. So I would say none.
What's the difference?
Remember, local is like close to you and like absolute is like over everything. So think about like local stuff, like there's things at Cathedral that like we hear about or we care about that like people in like California don't hear about or care about, right? So local is close to you, absolute is of the whole graph. No. Just, it will literally be like a graph and then like 2 lines. Name an equation. Okay, what about asymptotes? Are there any horizontal asymptotes?
0, 1.
There are at 0 and 1. Y equals 0 and y equals 1. Any vertical asymptotes?
No.
No. And then end behavior, remember we write it as x approaches negative infinity, y approaches something, and as x approaches positive infinity, y approaches something. Okay, this one we start in the middle and we essentially go outward. So I'm starting in the middle and I go this way. As x approaches negative infinity, what's my graph doing? It's decreasing. What's it getting closer to?
0.
0. It's getting closer to 0. So that means as x approaches negative infinity, y approaches 0. In the opposite direction, as x gets bigger and bigger, as x approaches positive infinity, what is y approaching? 1. Very good. It approaches that other horizontal. We've got a couple more minutes. I do, or I need to start another one. Alea, did you have one? Oh. What's the rest of them? What do you mean, what's the rest of them? Yeah. Oh, they're all on this paper. Like there's 12 of them on here. And so you just have to know all of their names and stuff. What's gonna happen though is like on the quiz, I'm gonna lead you to 9 of them. So I'm gonna give you 3 graphs, 3 names, 3 equations, and there will be 3 that you will have memorized or you will have known. That bonus, I'm just gonna say, like, do you remember which those 3 are? Yeah, Billy.
Some of them, like the name, so like you'll give us the name and then we have to write it down.
So I would know for all of them, picture, name, equation. What I would maybe do is flashcards. I would maybe put the graph on one side and then the name of the equation on the other. I think name and equation are often very similar, like sine, the name of the sine graph is just sine. And the equation is y equals sine x. So like that to me isn't a hard thing to memorize, but knowing what the graph looks like is important. Yep, I will try to do that next period. I don't have office hours tomorrow, so if you have any questions, either see me after school or ask a quick question. But we are gonna get started on the quiz very, very quick, just right off the gate.